Okay. This is recording. Then it is actually welcome to the physics colloquium if you are not from the physics department. And today I have the pleasure to introduce Dr. Clara Murgui from Caltech, that she will give our last semester, the last colloquium this semester. Clara is originally from Spain. She graduated at University of Valencia, the bachelor degree. Then she went to Germany and did a master degree under my supervision at the Max Planck in Heidelberg. And after that, when I moved here, she didn't like the weather here. And then she went to Spain, but still she was working with me, half of the time here and half of the time being a second supervisor in Spain. And she graduated only 2 years ago. And then now she's a postdoc at Caltech. She already had a faculty position at the University of Barcelona. Before that, she would go to CERN to work in Geneva. And just to make the introduction brief, Clara has been doing very well in this field. Presently, she won the prize of the Royal Spanish Physical Society for the best PhD thesis in particle physics. And she has been very well, and I'm very happy that she's back home.
Thank you, Pavel. Thank you so much. Well, it's a pleasure to be here because I always was there when you are sitting. So it's the first time. It's my first colloquium too, so it's an experiment. And I always have like a bracelet that gives me luck, and I lost it 2 weeks ago in that conference. So I don't know how it will go. So I'm going to talk about new ideas or perspectives to handle dark matter, like dark matter, which is below the usual masses that people look at nuclear recoil experiments, GV, so below the GV. And I would like to acknowledge, if this works, my collaborators who have been thinking about these ideas, as well, Yufeng Lu, who is a grad student at Caltech, Chris Pardo, who is a faculty at the University of South California, Jikun Wang, who is also a postdoc at Caltech, and Catherine Surek, who is also based at Caltech, and our experimental colleagues with whom we are trying to bring these experiments to life, which are Lee, Rana, and Gita at Caltech, and people from Yale, Jack Harris, and Yogesh Patil, which is his postdoc. So I'm going to start introducing what is dark matter, for those people that are not familiar with it, and why we are motivated in looking for it. So basically, everything we see, like us in this room, stars, planets, galaxies, is made of some constituent, like basic particles, which are, some of them are like building blocks in nature. Some of them have colors, some of them don't have. They are fermions, quarks, and leptons. And then there's some rules, some symmetries that tells us how to build this, how to organize these building blocks, which are the forces. No, in the forces have some mediators that tells us how to put these quarks and leptons. And those are the electromagnetic interaction, for instance, mediated by the photon, the strong force mediated by the gluon, and the weak gauge bosons. And the final piece, which is the Higgs boson that was discovered in 2012, the 4th of July, that is the one responsible of giving mass to these fermions. And this is our standard model. We are very proud of it. We can explain most of the phenomena we see in nature at low scale. And everything we see basically is made of these fundamental particles. But when I was actually about to present my thesis, I was trying to explain my mom what I was doing, because she sometimes doesn't know. And I was trying to explain her, and I said, look, everything that I've been studying during my bachelor and master's and PhD, it's only 5% of the universe. And the rest, we don't know what it is. Particularly, there's 5 times more matter. We call it matter because it interacts gravitationally, but we don't know what it is. We call it dark. It seems to interact with light. And we know that it's there. We have some probes that is there in different time scales of the universe, different sources. We know that there are some rotational curves of galaxies that are modified, saying that there's more matter than the one we see. We also have the CMB, that's the anisotropies, the power spectrum suggests the existence of this dark matter. It can also bend light, so we know that there must be some matter there bending by gravitational interactions light that we don't see. And also for large scale structure to understand the formation of galaxies, we need this kind of matter. But we don't know what it is. So there are many unknowns. There are a few things we know. We know it's cold, means it's non-relativistic at late times. It's pressureless, it dilutes as the universe expands. We know that it's distributed in galaxies in spherical halos. For instance, for the Milky Way, we know that it follows like a Maxwell-Boltzmann distribution. The average velocity is something like 220 kilometers per second. The escape velocity in the galaxy is 550 kilometers per second. And we know that locally the density is 0.3 GeV over centimeter cube. These numbers might be meaningless for you. It's just the information we have, and we may use it to try to detect it on Earth or around in our galaxy. And then we know that there should be some mechanism that sets its relic abundance to be 0.12. So this is the amount of dark matter that is freezed in the universe that we know is there and survived. So then when we ask ourselves, how do we build an experiment to detect this dark matter? We find that according to these constraints, we have 80 orders of magnitude in mass that we can be looking for. And this is very overwhelming. So we were having some discussion 2 weeks ago. There was a big conference in UCLA about dark matter, and people came, and there were two opinions in the audience. So some people thought, or had the mentality that we should take all the technology we have at hand and try to explore whatever we can. So being unbiased, open-minded, we don't know what nature has chosen the dark matter to be, so we should be open-minded. Just we have some technology we can use, we should explore the parameter space. And half of the audience was like, no, we have finite time. We have our lifetime is 1022, optimistically, and we have finite resources. So we should look for things that are motivating. And then, so I think both groups are right. So I would say if we have finite resources, let's look first for what is motivated. But if we have experiments that already exist for other reasons, and we can constrain the dark matter for free meaning you don't spend time or money, we should do that too, even if it's not motivated from the theory side. So I'm going to give you an example of each. Ones that are the atom interferometers that are there to measure other things and can be used to detect dark matter. But you'll see the parameter space is not the best motivated one, but we can use this data for free. And then I'll show you a motivated example, which are axioms that can also be searched in a tabletop experiment with hopefully not much effort. So of course, some paths here are more motivated than others. You might be familiar with WIMPs. WIMP stand from weak interacting massive particles, and are basically particles like the standard model particles that have the same strength as the weak force and masses around the weak force. So just as a naive estimation, if you don't know anything about dark matter, you would take some coupling that is more or less like the weak coupling, the Fermi constant, and you would put like a mass that is around the Higgs mass, for instance, 100 GeVs. And just with these naive expectations, you compute the relic density, that is the amount of dark matter that frees out. So this is the standard freeze out mechanism. Basically, dark matter annihilates. And as the universe expands, at some point, the universe expands faster than the dark matter annihilates, and there's an abundance that stays there forever. And this is what we compute. We know that it was 0.1. And with the naive numbers, we get already the 0.1. So this is the so-called WIMP miracle. That's why people were motivated about this kind of dark matter. Also, because you can search for it experimentally very easily, because the experiments, nuclear recall experiments, you can think of the same interaction that extends this relic density can also be used as a handle to detect it, because the same interaction that is mediating the annihilation can also, if you flip it, you can think of a scattering of dark matter with the standard model particles. So you can use this to try to detect it. And if you compute the cross-section with the same naive numbers, it might seem very small, but we are doing already better than that. So the constraints are 10 orders of magnitude better than that. They are touching the so-called neutrino floor, which doesn't mean that you can't look farther than this. It means that it's not a background experiment anymore. You have becomes a neutrino detector, your data detection experiment, nuclear recoil. So basically, if you want to understand the sensitivity of these experiments, when you go to heavier masses, we said before that in the Milky Way, the density is constant. So the heavier the mass, because the density is constant, means that the particles are more diluted. So the number of particles that enter the experiment are less. And this means that you start losing, the rate starts losing sensitivity because you have less flux of particles coming. On the other hand, if you go to light dark matter masses, there's a sharp cutoff in here. And this is because of the resolution that the experiment has. So these nuclear recoil experiments, which basically you have some atom, some material, and there's a dark matter entering and transfer some momentum, they have a minimum energy that they can detect, which is kilo electron volt. So the thing is, this will set up a lower bound in the dark matter mass, because the dark matter is non-relativistic. It can transfer a maximum amount of momentum, which is non-relativistic, is mass times the velocity. We know the velocity at most is the escape velocity in the galaxy. So it's in natural units, 10 to the minus 3. So this means that whenever this interacts with my nucleon, it will recoil, and the energy of the recoil will be inversely proportional to the target mass, which if it's a nucleon is going to be 1 GeV. So then this sets what's the lowest mass that these experiments, these nuclear recoil experiments are sensitive to, which is 1 GeV. This means that it's okay for WIMPs, it's perfect. But if you are wondering if you have a dark matter lighter than a GeV, you won't do well with these kind of nuclear recoil experiments. So these are the traditional WIMP experiments. You might have heard about xenon 1 ton, xenon and ton, Panda X, Blue Zeppelin. There's also the argon, the dark side 20K, dark side 10K. There are many collaborations based on these novel gases nuclear recoil experiments, and they are doing pretty well, but they cannot go below the GeV. So what do we have to do to explore other regimes? We need to change the energy resolution or the target. So some people have proposed, because this is also motivated. So I showed you before the naive numbers, but if the coupling of this dark matter with the standard model by some extra degree of freedom is small, you can have a dark matter which is below the GeV, and still, if it compensates the smallness of the coupling, you can still get the correct relief density. So it's motivated, but it's hard to look for. So you either have to change your target. You can think of electrons, recoiling electrons instead. This allows you to lower the access of light masses. You can think of ionization. You can think of semiconductors, which have gaps that are smaller, so more precision, more lower energy resolution. You can think of also of materials, semiconductors. You can change the degrees of freedom and think of collective excitations like phonons and magnons, and go to lower and lower and lower masses. So there are many proposals that hopefully in the future we will see whether we can explore this motivated regime. But today I'm going to talk about, well, these are some references if you're interested in. Today I'm going to talk about atom interferometers. And the nice thing of atom interferometers, these experiments are built, are already working. Some of them will be built soon. And the reason why they are built is because they want to study properties like gradients of gravity. They want to measure the fine structure constant very precisely, the Newton constant. These guys are accelerometers, and they want to measure gravitational waves. But they can also be used to detect dark matter. And the reason why they are nice for that is because they don't suffer from a minimum energy deposition resolution, because the way they will detect dark matter is through quantum decoherence. And you'll see that the quantum decoherence, it happens or it doesn't happen. So it's a very powerful tool to search for dark matter. And these experiments are there. So it's a byproduct. Like we can use them also for searching for dark matter. How these guys work? Theoretically, it's very easy to explain. I guess for me that it's harder to implement, but these guys are doing it, and it's very impressive. So you take a cloud of atoms, take your favorite material, a material that has a definite ground and excited state, an optical transition, and cool your atoms all to be in the ground state. Okay, and then you apply two lasers. So the difference between the two lasers in frequency perfectly matches the gap between the ground and the excited state. So the longer you apply the pulse, the more atoms will start to be excited and move to the upper state. And at some point it will populate and it will start decaying to the ground state. So this follows the distribution of the population, follows the frequency that is called the Rabi frequency. And if you want to know more about it, it's super well explained in my lecture, second edition, chapter 6.8, for me was very useful. And then you can, depends on the time that you apply the pulse, you can control where your population is. So that's how people name these pulses. Pi half pulse means that the product of the Rabi frequency times the time you apply the pulse is pi half. So this means that your population is going to be pi over 4 is 1 over the square root of 2. You're going to split your population in the ground and in the excited state in a quantum mechanical way. So the system is quantum, it still can interact with itself. It has a superposition that is non-zero. So these lasers really act like a beam splitter, and they split your population in ground and excited state. And of course, the guys that are now in the excited state, the blue guys, have absorbed a quantum of light, so they will recoil with some velocity. that is proportional to the gap of energy over the mass of the atom. So in this diagram, which is distance over time, they will separate macroscopically from the purple population. And at half of your experiment, you apply another pulse, which this time is pi, means that you apply it double time as before. And what it's going to do if you do the algebra is flipping the population in the ground and the excited state. So now the blue guys are in the ground state, the purple guys are in the excited state, and are the purple ones the ones that will move, while the blue ones will stay still. So this really acts like a mirror. You have the same evolution and exactly the same at you pick half of the time of the experiment. At the end, you apply another pi half pulse, which is a beam splitter. You make them all back to the ground state and you measure. And then you expect to see 100% probability of your atoms in the ground state, and a white port and a black port, 0% probability in the excited state. So this maybe resembles you to a Mach-Zehnder interferometer. Instead of light, we use matter. And instead of using matter to split light, we use light to split matter. But it's really the same. We have a beam splitter, we have a mirror, we have a beam splitter, and we measure. It's exactly the same thing. So when this is perfect, and this works perfect if it's a closed system, and if the laser momentum is exactly the same as the gap between the ground and the excited state. That's why it's useful to measure the fine structure constant and all these properties. But what can happen if you are in an open system, it's better that we use the density matrix. That's a tool to describe a system. It's basically an emission matrix, positive definite trace equal to 1. And every quantum system has a density matrix associated with it. But not every density matrix corresponds to a quantum system. Density matrices are more generic. They can also describe mixed states, classical states, or almost quantum states. So basically, the way of this statement is if you diagonalize this matrix and you get an eigenvalue 1 and the rest 0, this is a pure state. If not, it's not a pure state anymore. Basically, you lose the possibility of the system to interact with itself, the quantumness of the system. So what can happen, because in this second path or in the first path, you are separating macroscopically the two-wave packets. What can happen is that you have a piece of dust or a dark matter or a solar neutrino, something that resolves one of the paths of the wave packets and not the other one. So you are knowing in which path you are losing the quantumness of the system. And this is quantified by this gamma here in the density matrix in the diagonal elements. And this gamma is called the decoherence rate. And it basically has a real part, which is e to the minus s, and an imaginary part. The imaginary part is a rotation, doesn't change anything. It's a unitary transformation. You can think of a rotation if you have if you diagonalize this row, you have a 1 and a 0 is a diagonal matrix. Doesn't matter how many times you rotated it, you won't change this feature. But the real part is going to suppress this called visibility or contrast, and you will understand why in a second. But this is going to go from 1 to 0. So if it's 0, it's a pure classical system. If it's 1, it's a pure quantum system. If it's somewhere in between, it means that it's a system that has lost partially the ability of interacting with itself. And this is caused because of there had been something interacting with the system. So this is the fourth factor that quantifies how much the coherence and interaction causes on the system. And this fourth factor is an exponential of an imaginary Q times delta. It's a sinc function. It's like almost like a Heaviside function. And what it tells you is how two magnitudes relate. The momentum transfer of the interaction with respect to the distance of the two clouds. That's the main thing. And I'm going to emphasize several times. So for you to keep the idea clear, you have two clouds separated by a macroscopical distance, delta x, which can be micrometer, can be even meter, depends on the experiment. And then we will have some interaction that can be dark matter, can be whatever is in the environment. If this interaction does not resolve in which cloud we are, we don't cause the coherence. But if the interaction has enough momentum that the de Broglie wavelength resolves is less than the distance, then you are picking one of them. So you know in which path you are and you lose the coherence. And the same thing will apply if you zoom in. The cloud has many atoms. If you do not resolve the cloud, you get an n-squared enhancement because you can't distinguish which atom the interaction is happening. You get once you sum over final state, you get an n-squared enhancement in your rate. If you resolve, you lose it. But the same applies to the atoms, which has a number of nucleons. So if the interaction happens at the nucleon level, you might still get a small a number of nucleons square enhancement or not. And this is all about momentum transfer and distance of things. Size of cloud, distance of the two clouds, And this is the main trick. There will be some force factors that act like Heaviside functions. Either you are in the coherent range or you are not. So this is the force factor, how it looks like, the same function. You can see that it's either 1 if you resolve the atom, if the momentum is larger than 1 over delta x. If it's not, you do not, the coherence rate goes to 0. So the longer, the more separated are your two clouds, the larger the chance that something decoheres them, because delta x is larger, so there's a wider range of momenta that can cause decoherence in here. So how this is detected? So imagine that the dark matter interacts with one of my paths and decoheres the system. Whenever we measure, we won't measure 100% and 0% anymore. We will measure a fringe. So either you do several measurements, or you use a laser that has a gradient of different angles. With one measurement, they can already get the fringe. And what you will see is that instead of this black line, which would be 0 decoherence, the amplitude is reduced. And this is due to the real part of this, what I call V, visibility or contrast. Visibility meaning the visibility of the fringe. So it's either 1 or it goes to 0, depends on how much the interactions are decoherent in the system. So then we can generate an SNR, we can know what's the precision of the experiment, or some statistics, we know what the background we should expect, that might depend on systematics or in your whatever background you are exploring. And then we can put a constraint on the dark matter by knowing what's the rate or how strong we expect the dark matter to interact with the system. We will put some constraints to the dark matter phase space. And we should be careful because as we were talking, I don't know if I was talking to Fer, with who I was talking about before, but we have to be careful because it's very easy. If we don't see anything, if we see the full print, it's very easy to rule out things. We say, okay, there's no dark matter, because if there was a dark matter, we would have lost part of the visibility. But if we lose part of the visibility, it's going to be very hard to say this is due to dark matter, because there are other sources in the environment that might cause decoherence. For instance, solar photons, solar neutrinos, dust, interstellar dust, because these experiments will be set in the state, and also cosmic rays. Like there are many sources that could decohere a system. So that's something we are doing now. We build, some of them are not dangerous at all. Some of them might be. I highlighted here the cosmic rays and the solar photons. So these people didn't take into account for the atom interferometers, and we want to point out that also if they want to study other things, this problem they will also have. Doesn't matter if you study dark matter or if you want to study, use it to detect gravitational waves. You need to have, you need to control these backgrounds, and that's something that hopefully they can shield these from solar photons, and it might be fine. But it's something that can cause decoherence. So there are ways to distinguish whether it's dark matter or some other source by directionality, and there are tricks that you can use for comparing one atom interferometer on Earth and one on space. But this is something that we should be careful. So what's the rate? The rate is the inverse of the lifetime. Basically, this S that you see here is the rate of interactions per mass of the target per time. So this will tell us what's the probability of reducing the visibility from 1 to whatever the dark matter causes. This will depend on the dark matter ingredients, density of the dark matter, we know 0.3 GeV over centimeter cube on Earth, the mass, and the target density. So if it's rubidium, it will be the density of the rubidium. We know the distribution of dark matter, the flux follows our Boltzmann-Maxwell distribution. We know the main velocity, we know the escape velocity. And this is the model dependent part. So the rate will depend on your particular model, your favorite dark matter, whatever, how it interacts with your nucleons. But this is something that I can take a scalar dark matter, a scalar mediator, and compute my cross-section. You can have a different favorite model. What I will do is just call this thing a constant that I call sigma bar, and I take out of the integral, and I parameterize whether the mediator is heavy or light by some form factor, so I recover the Q-square dependence or not. And this is something, the only thing that enters in the integral. So I just call this thing that I don't know what it is, a constant, and I give you some constraints. So then if you have a favorite model, you compute your constant and you translate it to your constraints.
I don't understand a word.
Scalar dark matter, but if you want to look for a vector dark matter because you have a model that you think that it's like that, it would change some numbers in here,
Okay,
and you can read out easily the constraints. So that's a trick that we usually use to make it more model independent. And the form factor that we were discussing, the same function. If
tomorrow I'll tell you all about the
the
concert.
decoherence, if you do not resolve, this goes to 0. So in here
Okay,
also
thank
the
you.
form factor of the target, what we were saying before, there's a number of atoms. If you do not resolve them, you get an n-square enhancement, the rate is.
Okay.
If you resolve them, you lose it, but you also have the atoms. And it's all about this
Good night.
momentum transfer and how it compares to the main elements in the atom interferometer, which is the distance of the clouds, the radius of the cloud, the number of atoms, and the number of nucleons that this atom has. So, and of course, the time the experiment runs.
You don't care about this
These are the
colloquium.
experiments we consider.
Don't
There are
talk to
more.
us.
We consider some experiments on Earth. We
Spanish
took them
accent.
as a proposal
The way I listen to watch.
from 2014, actually, but we wanted to have an example. We were interested in space atom interferometers, but we also wanted an example on Earth. But then the referee told us that in Stanford, they have a 10-meter power fountain of free-falling atoms, and it's already working. Because that's going to be the prototype of MAGIS that will be used to detect gravitational waves at Fermilab. So this is something of, actually, we are now collaborating with these people in Stanford, and they are very interested. So we included this also in our
Oh,
calculation.
I'm so glad I
And in
did.
space, we were in contact with people at JPL, next to Caltech,
It
they have
shows
PAL, which is the
a
cold
little
atom
part
laboratory.
of the black
So we know
void.
the numbers
in the
that you have
electron
to use
hole.
for activity, what's the usual systematics that we have. And they are going to improve it to BPAL, which is a higher number of atoms, Bose-Einstein and condensate, these clouds. GDM is if I remember properly, NASA Advanced Initiative Concept Phase 2. That is something that we probably have within 3 or 4 years because it's not approved yet. It's very ambitious. Also, it's going to be hosted by JPL. And macro is another atom interferometer that they have a white paper, the collaboration. Jess Riddle, who was one of the first who pointed out the decoherent effect in this collaboration. And hopefully in a couple of years, it's launched to the space. So these are the limits. And for different atom interferometers, that's by just imposing that the visibility is bigger than half of the fringe, then what's the constraint that you would have in this cross section, in the way, in the probability of the dark matter to interact with
the
the
camera.
So it seems a lot.
Yes, the
But now
boy.
let's put it in context. What are the other constraints that we have from other experiments? So coming back, so for these cross sections that I showed, I assume different relation between the mass of the mediator, the guy that mediates interaction between the dark matter and the nucleons, and the dark matter mass. All of them are light. Light meaning they're even lighter than the dark matter. So for light mediators, we have some constraints. For instance, this interaction here, you have dark matter interacting with nucleons. You can also think of having, so there will be terrestrial, astrophysical, and cosmological. I'm going to focus first on terrestrial. You might have this scalar also mediating interaction nucleons with nucleons. And this you can think of it as a long-range force, because this is a very light mediator. You can compute the Yukawa potential, and it might mimic like a fifth force. So this is something like a gravitational modification of this Newton potential. This is something that has been explored, and there are many, many strong bounds. So you can map this, and you can set constraints on this Yukawa, on the coupling between the nucleons and this light mediator. And this is going to already kill part of your parameter space, because you cannot, so this is the effect of having a light mediator. This would mediate a long force between nucleons, and this is something that has not been seen. So this translates into constraints. And we also have to check the stars, because if you have a light mediator, it might be cooling or accelerating the rate at which the stars cool. So this constrains also the parameter space. And finally, if you look at the other coupling, which is the light mediator with dark matter, it might mediate dark matter self interactions, which are also constrained by the Ballet cluster. So then if you put everything together, you can see that all your parameter space is already rolled out. So that's what I was telling you. This is not motivated from theory, but you don't know if the dark matter is composes the whole relic density. It might be a subcomponent. So if it's a subcomponent, if it's something like 5 and 10%, and the rest of relic density is a primordial black hole, or are part of it are a small part are neutrinos, or there might be other particles, you can see something if it's a subcomponent, because then the bounds are way more relaxed. So because it's free to check out this data, they are taking the data anyways, we should try to learn as much as we can from these experiments, because they are there, and it's a pity not to do it. But it's not, these experiments wouldn't be built to detect dark matter, because it's not the most motivated point of view, part of the parameter space. So then if we go even to lighter, now I'm going to show you an example of a motivated case. We go to ultralight dark matter. There's a point in this spectrum in which, you know, when the dark matter mass is heavy because the density is constant, dark matter is diluted. So then the de Broglie wavelength associated to the dark matter is very small, it fits in your detector, things happen punctually in a localized space, and this is like a particle. But if the dark matter is light, what happens is the density is constant, the occupation number grows and grows and grows and grows. And then at some point, it starts behaving classically like a wave. So when this is below 30 electron volts or something like that, dark matter behaves like a wave, and you lose the connection of dark matter annihilating to nucleons or to standard model particles, but there are other mechanisms to set the relic density. One of them is the misalignment mechanism, and basically through the oscillations of this wavy dark matter, the way it oscillates, it behaves like non-relativistic dark matter and can contribute to the relic density. But then you lose kind of the connection between the standard model particles, and it's hard to look for this. Still, there are searches. There are atom interferometer searches of wave dark matter, not particle dark matter, as I was talking before. There are laser interferometers in the gravitational wave experiments looking for scalar indector dark matter, but it's a bit hard. So there's one candidate in this region that has a motivated connection to the standard model, which is the axion. And the axion that you might or might not have heard about it plays a twofold role. It can be a dark matter candidate and can also explain the so-called strong city problem. So just in drawings, I'm going to try to explain it in a minute. Basically, the Lagrangian of the standard model, the masses of the quarks can have a complex phase. And before we thought that this complex phase could be rotated with an axial symmetry, because it seems that the Lagrangian naively is invariant under a rotation and axial rotation. But then people like Weinberg said, okay, if this was the case, at low masses, when we have the three light quarks up-down strings, we would expect a U3 cube symmetry, and we would expect 9 Goldstone bosons. But we have only seen 8 pions. What happened with data prime? Why it has heavier mass than the others? And then Toft say, okay, this is because it was never a good symmetry. It was broken at the non-perturbative level by the QCD instant. So we are really summing two things. One is the phase of the quarks, which is order 1, the CKM phase. And one is the topological angle that is there, and it has a physical meaning because it labels in which vacuum you are, which of the topological solutions you are. So it's a term that might be different from 0. Are two big things that are summed and have to be extremely aligned to be 10 to the minus 10, because you haven't seen an EDM for the neutron. So this means that the quarks are extremely aligned. It seems that QCD preserves CP, but there's no reason for that. So this is the possible. Why QCD seems to preserve CP. So there are ways out of this, and the axion is one of the most motivated ones. You introduce an axion with a symmetry that behaves more or less like the axial symmetry, and this guy can swallow these contributions, and you end up with 0. So you end up with a perfectly aligned EDM for the neutron. And it's nice because it has a very nice prediction, it's got a very nice connection with the scale at which the symmetry is broken, that gives you a line, a very definite line, in the coupling of axons to photons depending on its mass. It's very challenging, but we like to know where in physics is. If it's there, it's going to be in the plan. So people are motivated to look for it, and we have the connection to photons, so we can look at optical experiments. And already some haloscopes, which are experiments that assume that the dark matter is made of axions, are already touching this line, like ADMX, are optical cavities, high-star as well. But then you can see that the range is very focused on micro-EV. This is because they have a cavity of some length, and they have to match the length of the cavity to the axion mass to be on resonance. So it's hard to tune the length to go to very high, like longer cavities to explore other regions of the axion mass. So it's like you have to think of the axions being waves crossing. We are in the dark matter halo. These waves are coming, and you have a radio. So you have to tune your radio to find to synchronize it with the axion wave in order to hear it. And that's what these experiments are trying to do, but it's hard to synchronize when you have to change the length of the cavity. So there are many projections. These projections are based on decoupling the length with the axion mass. For instance, dark matter radio, you might have heard some colloquiums or some talks about it. There's DSRF cavities, which basically have, I mean, I could explain them nowadays, but it's like they have final states which are nearly degenerated, and you can put the axion on resonance and decouple the length with the mass. Tunable plasmas, dense, which is utilizing both in there, one of our collaborators, which is for very low axion masses. But if you see this was taken from snow mass, you can see that apart from this guy, the last line that I put it in opacity lower because it's very hard, it requires very heavy magnets. You can see that the sweet spot for detecting a post-inflationary action, according to some simulations, it's in a region that is hard to build a cavity to detect. So I'm going to talk about this idea of axial optomechanics that I proposed together with Yipun and Catherine last year that might be able to access this range. It's challenging, but our experimental colleagues will tell us how challenging it is. Right now, I'm trying to convince people to get involved into these cavities because I think it has some potential to reach it. So I'm going to just give a very brief review of optomechanics. And I don't know. Okay, I think I'm okay. So basically, you have a cavity of some length L, okay, and you pump it with a laser, and then this laser, there will be light going back and forth and being reflected by the mirrors. And depends on the frequency of the laser, these mirrors, once they will interact constructively or destructively. So if the frequency of the laser, the wavelength of this frequency, it fits half of these wavelengths, and if the number of them perfectly fits this length, the wave will be a standing wave, and your photons will stay in the cavity. Otherwise, they will just create thermal, so they will just appear. So this defines what the optical modes are, and are multiples of this pi over L, which is usually called free spectral range. So now you fill the cavity with some material. You can think of superfluid filling, for instance. And if you fill it with some material, the light is causing some pressure, and it's acting on the material changes the refractive index, and it acts on light. So this interaction between light and mechanics is what is called optomechanics. And this is proportional to this alpha here, which is the polarizability, the ability of the material to generate a dipole, to interact with light. So in this naive plot here, this is like the PSD, the power spectral density of what you measure. If you pump your material with some photons, it will reflect some photons which are at the frequency of the laser. So now you can think of the material as an harmonic oscillator, and it will create and destroy excitations of the material, which we call phonons. So basically, if you quantize your electromagnetic fields in your density of the material, you have the quanta of light, which are the photons, the annihilation and inclusion operators of photons, and you have the same and analogous to this but acoustic, which are the phonons. So two photons can interact with a phonon proportional to this coupling G naught, the optomechanical coupling, which is proportional to the ability of material to form a dipole. So basically, you can have two things happening. The photon of the pump laser interacts with the material and creates a phonon. And because you create a phonon, the phonon will carry some energy and will redshift your photon. So it won't be in here, it will be a bit redshifted. The amount, you can just go to kinematics, compute energy and momentum conservation. It's one-dimensional, it's very easy to see that the phonon will carry twice the momentum of the photon, photons will be back-to-back, and the amount of energy that this phonon carries is twice the frequency of the laser times the speed of sound on the material, which for superfluid helium is 10 to the minus 6. So if you start with 200 terahertz frequency, you will end up with a splitting, which is 10 to megahertz or the megahertz. So it's 6 orders of magnitude, 1 billion times smaller. And this thing here, this is the consequence, this is the photon that has been redshifted because there's a phonon that has been created. And in the same way, if you absorb a phonon with the right kinematics, you will blue shift your photon this time. So you expect to have these two side bands around the laser because you have a material. If you remove the material, you only have the green line. If you put the material, you expect to create and destroy phonons, and then you will have the Stokes and the anti-Stokes lines. This rate at which these processes happen is proportional to the mechanical coupling square times the number of photons from your laser. This is because your laser is a coherent state and it enhances the rate linearly with the number of photons. If you want to know what this number of photons is, let's think of the light traveling in the cavity. The light travels a distance L and is reflected by the mirrors. And this, every time it happens, the mirrors are not perfect, you lose part of the population of photons. This will depend on the transmittivity, on the reflectivity of the mirrors. So the more times it reflects, the more population you lose, and you can estimate what's the lifetime of the photon inside the cavity. This will depend on the speed of light, which is 1 minute, will depend on the length. So the longer it is, the more stable they will be because the more they travel without being lost. And then it will depend on the reflectivity of the quality of the mirrors and the absorption of the material. And this is what is called finesse in optics. It quantifies how good a cavity is. So then the density of the states, that the free states will be a delta function, it's modified by the finite lifetime of the photons, and it's a Lorentzian. So basically it becomes a Lorentzian, means that your population is distributed around the optical modes, but it follows a Lorentzian shape. Okay, with the width is just the inverse of the lifetime, the rate of loss of photons inside the cavity. So basically, if you are, so the number of maximum photons you can have in this Lorentzian, proportional to the power, the lifetime, and inversely proportional to the frequency. So if you're clever enough, you will put your laser in one of these optical modes. If you are not, and put your laser shifted with respect to this optical mode, you will pay a price. The price of being in the tail of the Lorentzian. So we bet that if we want to enhance the rate, this number of photons, we want it to be as much as we can, the maximum, we will pick the frequency of the laser to be in one of these optical modes. Okay, so what can happen now, if there's an action in the environment and it interacts, the action has a coupling with the two photons. And you're going to have this interaction with there's a photon mediating the interaction. If you think of it as an effective interaction, the action is there. And what it's going to do, because the action, if its dark matter is non-relativistic, it won't modify the momentum. The momentum conservation is the same. In the cavity, this is called overlapping of the modes. This is still the same. It doesn't spoil the overlapping of the modes, but it shifts the energy. In the energy conservation, the action energy, the energy that the action carries is its mass. So it will shift the Stokes mode that you would have without the action exactly by the amount of the action. So if you can see this peaking here, you will know, compared to the other one that you know what it is, because you know what's the energy, this omega m, you will know what the action mass is. So how can we look for this? Well, we have to overcome a huge suppression, because this coupling of the action to the photons, if it's the QCD action, is extremely suppressed, also because of the amplitude of the action oscillations in our galaxy, it's very small, 10 to the minus 2. So we need to overcome this. What can we do? We can pump the cavity, we can excite the cavity with some population of phonons. They can do it extremely precisely with a piece of material. They can decide where the phonons are and populate a mode. And if this mode corresponds to the final mode where the final photon is being created, it will enhance the rate by the number of phonons that we populate. So then we can get this N5 here is the number of phonons that we can populate the cavity with. This will help to overcome the suppression coming from the action interaction. So the rate is going to be coupling square, suppression of the action that is killing us, and then number of pumped photons, number of phonons that you can pump the cavity with, in a convolution of two functions. One is the Boltzmann distribution of the action, the other one is the Lorentzian due to the optical mode where the photon is being created. So when we compute the SNR, we want to quantify how the signal is bigger with respect to the background. This will put some constraints on GA gamma gamma, which is the coupling of the action to the photons, that will depend on the action mass, cavity properties, which means length and finesse, laser properties, which means frequency of the laser and width of the laser, material properties, which means density, speed of sound, and permittivity in the vacuum. And then we can have two cases. So if the action mass is very light, the Boltzmann distribution is almost a delta function. So in the convolution, it will win the Lorentzian, and then your rate will follow a Lorentzian shape. So we will scan over the width of these optical modes to don't lose in sensitivity. We will only lose 1 over square root of 2 if we do that. And this will define how long we have to scan or how far we have to scan in action masses. Put the phonons in one frequency, we scan for the action mass, we change the phonons a little bit, we measure again, because wherever we put the phonons will define the action mass that we are looking for. Because we are looking for a peak, we don't know what it is, we populate the cavity at different frequencies with the phonons, and we are searching for different action masses. If the action mass is heavy, it's the opposite. The Lorentzian becomes like a delta function, and the Boltzmann distribution dominates. The Boltzmann distribution becomes wider and wider as we go to heavier action masses. This means that we can scan even bigger ranges of action masses in a heavy action regime. So some numbers. These people here, Jag and Yogesh, are our colleagues at Yale. They have a cavity of superfree helium, which is 100 micrometer long. It has a finesse 10 to the 5, and they use pump lasers microbats. So they are studying an empty cavity of phonons, creating a phonon, and studying the properties of this phonon. And this is their cavity. And what they could do easily, if they had money, is to increase this cavity to 1 meter, use VAT power, and go to finesse 10 to the 6, because they just said that they hardened light and build this into a 6 finesse cavity, which is very impressive. And they could easily populate the cavity with 10 to the 14 phonons. So the first time I heard this, I was thinking, this is crazy. But apparently they can do it, and they could even pump it with 10 to the 19, because that's the limit where the superfluid helium starts to lose its harmonicity. Then we have these people at Caltech, which are working in LIGO, and they are interested in building a cavity with silicon. They want to study some properties of silicon, and they are thinking of these numbers, 10 to the 19 phonons, 10 to the 16 photons that come from using 1 watt of power in 10 centimeters, 10 to the 6. And that's something that we want. We are actually, yesterday we had a meeting and I missed it, but we are working with them, and hopefully we can find some agreement between us, because they are interested for some other reasons. We're interested from the action, but we can build something together, and it's at Caltech, so we don't have to fly to jail every time. And GQuest is another interferometer being built from something that Franklin is suggesting, some fluctuations of the vacuum. And this experiment is very ambitious, but apparently they are getting there. They want to use 10 kilowatt power, 5 meter cavity, but this is not filled with any material. So I doubt that whenever we fill it, we can keep these huge powers. Probably we'll have to lower it to 1 watt if you want to keep the thermal noise quiet. So kind of noises we can have. This purple peak will be the action, and the red and the blue are the usual peaks you have because you are filling your cavity with some material. We can have thermal phonons, which means that if you pump the cavity with some power, you will excite it. There are some phonons that are created in your acoustic modes, and they might mimic the action signal if they are in the wrong place. So this is something that you have to keep the quality cool if you want to see this purple line there. There's laser frequency noise, which means that these Lorentzians you see there, the green, the red, and the blue, they will have some tails. You need to make sure that the action signal is above the tails if you want to see it. Otherwise, you won't be measuring the photons from there. And also the dark count rate of your detector. The detector is a scintillator. It's not perfect. There might have some dark count rate that you have to be above that if you wanna associate this photon with the action signal. So focusing on, you can keep the cavity quiet, you can keep this dark count rate good, but the laser frequency, just to show you better what it is, if you focus on this action signal and you zoom in, this might be the tail of the stocks or the tail of the pump laser. You need to make sure that this is below the peak, and this can be solved by putting different cavities, one following the other, so that the Lorentzian is not a Lorentzian anymore. It becomes more suppressed by a higher power. So the more cavities you have, the more you can suppress these tails. And actually with 3 cavities following each other, we will be able to forget about this, as long as the action mass is heavier than micro EV, because that's what they need to apply this kind of filters. So this is a plot of what we can do for silicon and for quartz, for powers that are 1 watt, 5 watts. And the last line that touches the QCD line is 10 to the 7 finesse. This is something very ambitious, but the first curve is more optimistic, more realistic. So that's something these are theoretical curves, so we need to build the cavity, we need to know whether this is consistent with the noise we are expecting, and that's something that hopefully we will do together with the help of our experimental colleagues. And these lines I'm showing here, these black lines, is just the superposition of the different scannings you do. So when you do a scan, you are testing the action mass. The farther you go from the action mass, you have things out of resonance. So you pay the separation layer of the Boltzmann or the Lorentzian distribution, depends on which region you are, the action mass. And these lines is the superposition where you can really see this is ruled out, not the peak, but whatever. It's a 1 over square root of 2 if you do it properly. And these are some other plots where we use a superfluid helium, but you can see that the power we used in here was 10 kilowatts. Now, from what I learned after we published this paper, I think this is too optimistic, because you would actually burn the mirrors. This is a huge power. We took it because GQuest was using that, but now we are talking with the people there, and I think we should keep it to 1 watt, but still silicon and quartz might be the materials that we use for detecting the actions. So I just want to emphasize that it's very important to think what we have at hand, the technology we have at hand. Maybe some experimentalists are interested in building this for other reasons. And there's this connection between fields that is stupid. Like learn about them, and they might also benefit from searching for actions for that matter. So it's a symbiosis at the end of the day. And it's important to know or to be aware what we can do with all these tabletop experiments and all this technology, condensed matter, optics that we can use to detect either light dark matter or axions, and particularly atom interferometers, which have some benefits, which exist. They are there, there's no minimum energy deposition, and we can have a coherent enhancement. So if they could keep more atoms in a nucleus, in one of these clouds, the more the atoms, the better the enhancement. And maybe we could even reach interesting curves, even if we are considering only one particle to be the whole dark matter, which doesn't have to be the case, but it's something we can use to constrain the parameter space. And in these axioptomechanical searches, it's interesting that the axiom has a very specific kinematics. There's no other dark matter, as far as we know, that can mimic this effect, because it couples to photons, and it's non-relativistic. This dispersion relation is the opposite as a phonon. The energy is way bigger, while for the phonon is 10 to the -6 suppressed. So it's very hard to mimic, and it has very powerful properties. You decouple the length of the cavity with the axiom mass, because what you are tuning is where to put the phonons, not the length of the cavity. It's almost a background tree experiment. Still is tough because it's very suppressed, this peak, but there's nothing else that is mimicking this effect. And it's complementary to other axiom searches because it might allow you to go to heavier axiom masses, while for other cavities or other proposals, this is in principle tough. So I think I finished. I don't know if I make it on time.
Thank you for this wonderful colloquium. Questions? I know it's summer, but it's time to make questions.
So this is very cool stuff. Is there a fundamental limit to digging down to where you get to, you can push that curve all the way down to the yellow, QCD axion, or is that a materials power, kind of thing, just where things are at right now?
Yeah, so it's the power is a problem because the higher the power, the higher the temperature in the cavity, and then you start paying the price of the background of this having several phonons. We are thinking of changing materials because this optomechanical coupling will be proportional to the permittivity in the vacuum. So this is the rate. For instance, we were considering for tritium is 1.057. We were taking quarters of -6 suppression here. While if you use another material, this might be bigger. So it's important to think that, of course, this is also proportional to this. Everything is proportional to the speed of sound. The speed of sound for quartz, for instance, is bigger than helium. So there are some properties also for quartz. It depends on the material. You can pump more or less phonons to be consistent with non-spoiler of your material. So this all has to enter. We have to find what's the optimal area for that. So this we still might get a couple of orders of magnitude by picking the right material. But power is complicated. Length, you can go to bigger lengths. Bigger lengths allow you to pump more power, but then things are harder to control, and it's also more expensive to fill everything with, I don't know, diamonds or super helium like the emitter cavity. It's going to be challenging. And then what else you can change? The finesse of the cup. The better the finesse, the better the rate. But it's hard. Depending on the material. I think for helium and CC, silicon is hard because it's very absorptive, and quartz more intense. So it's all we are still learning from experimental stuff. We can do the numbers, they give us information, we put it on the rate. We know that, but we don't know how the materials behave. So it's something that we keep talking to them. And now they are interested, so we are writing something that hopefully we can make up a proposal. It makes sense. I don't know if we will reach the line, but there are also ALPs, these axion-like particles that might be interesting. Although they appear in other models, we're sensitive to them. So maybe it helps to exclude some part of the parameters of these particles.
Any other questions? Students? Remember, it's mandatory to ask questions.
Earlier, the topic of that distribution function.
Uh-huh.
So
Because the way it's distributed it follows a spherical distribution around the galaxy, and through the vital theorem, you find that follows a Maxwell-Boltzmann distribution, and you can compute what's the average velocity, and the escape velocity depends on the galaxy. And yeah, this is textbook thing for dark matter. Very useful when you put experiments on Earth.
So I've never seen a talk start when first experimental. Can you tell us a little bit more about that?
About what?
About the relationship with experimental.
So we started talking to people at Yale because we heard a talk about Jack Harris and they had a cavity. So we wanted to know more about this. And then we started Skyping with them, with particularly him and his postdoc. Then we started also to travel into Yale and discuss with them in person. And they have a different, the motivation of them is different. They want a bigger and a better cavity. I don't think they care so much about axioms, but it's something that goes in the same direction. We both want this cavity to happen. So also the way they work is a bit different. They are slower than us. So we were more like pushing things and they were like, oh, okay, we have to check this, we have to. So that's why we decided to write a paper with the theory idea, like the proposal. And now we are writing with them something which is a particular proposal of the cavity with a particular medium and length and a particular point in the parameter space that I'm showing. Have different lines, different lengths. We will focus on something concrete, which then is useful to know how to control the backgrounds, because it depends on which length or which finesse, which power you're using, you have different backgrounds that dominate. And with people at Caltech, we send them an email, we send them the paper. Yuta Mishimura is working in dance experiment, which is very similar. They don't have phonons, so they also have a laser, and they don't have a magnetic field. They use two lasers, but then whenever they have the axiom, because they have a Lorentzian here, if they want this to be on resonance, they need to be, the axiom mass has to be smaller than the width of the optical mode, because otherwise they lose from being on the tail of the Lorentzian. So they are sensitive to masses which are below 10 to the minus 10, which is very small, below 9 MeV. But they have this experiment in Japan, it's working. So he wrote to us. He was very interested because they were thinking of implementing the phonons, which would allow them to extend the line to go to heavier masses. And we started collaborating. Rana got interested, and that's how we started this collaboration we are now also having. And yeah, and every time I give a talk, there's always someone that comes saying, hey, we have this experiment, this happened to me. And they seem interested. Also for other reasons. I don't know if they really care about the axiom, but they are interested in going to better cavities, better technology, better finance, and explore, basically.
Question there?
Related to that question, for the people designing these atomic interferometers, the main interest is what gravitational waves.
Depends on which one. So I think for MAGIS, the one in Fermilab is gravitational waves. They will do very well at that. But other experiments like ION in the UK or other atomic interferometers, they were interested in studying gradients of gravity and measuring with more precision Newton constant final the alpha electromagnetic, because this is, if there's something different from what you expect, you will see some kind of coherence. So they are accelerometers in they are built for other reasons. Yeah, it can also be used for dark matter, so it's cool, or anything that can cause the coherence of these wave files.
Is the axion detection by one?
The axion detection in this case depends where the peak is. If the axion is very light, that's why we focus on masses that are above micro eV. If the axion is lighter than that, the lighter it is, remember you have your laser, your pump laser at 200 terahertz, and then you have your Stokes, that is the peak due to the fact that you have a photon and you are creating a photon. So this red sheets your final. Okay. But then if you have an axion, the axion is injecting energy. So it's shifting this by the amount of the axion. So if the axion mass is light, imagine that this is something lighter than even the width of these peaks, and it's in here. You won't see it because it's killed by the tail of your other peak. Because we're always, doesn't matter if you have an action or not, this interaction is always happening. So you expect to have these peaks. And the palm plays it as well. There are photons that are being reflected that don't create or destroy any photon, and they will be at this frequency. So you can't have sensitivity of this. To have a background experiment, you need the action has to be heavy so that this peak is far away from the space. And really, if you measure a photon here, you know it is the action. But apart from that, if you put a big power, you have thermal noise is populating every point in the parametric space for the photons. This can be complicated, so that's when you complicate full. And then there's also the dark contrary, the detector is not perfect. Maybe every 1 second you see a count, and then the action should be, or the GA gamma value should be big enough for this interaction so that it's above the dark contrary of the detector, because if not, you will see a photon, but because it's in your noise of the detector, you don't know if it's the action or it's because your detector is not perfect. So you need the rate to be bigger than that. That's what is limiting this curves in the gamma. It's hard because the photon problem reactions is very scarce. So it's hard, but I think there's chances that we can. That's the line. At least for the interesting parametric space that other experiments cannot reach.
Gemma?
So for the forward, instead of all of the astrophysics was supposed to be attributed to the signal. So how would you expect the light dark matter is supposed to be different?
It won't be different, but so if you know very well what your backgrounds are, for instance, we have computed that the solar neutrinos, they don't know anything, they think of here the amount of visibility reduction is 10 to the minus 26. So you notice this, you can't measure this. It's very small because they are neutral, they interact with the C boson, the C boson is a heavy indicator, and then if you compute the rate, it's very suppressed. For instance, dust, interstellar dust, also you can think of a geometric cross-section interaction, the balls of dust interacting with the clouds, but the abundance of dust is not big enough. You get a similar, maybe 10 to the minus something like 10 to the minus 10. Visibility reduction is nothing, so you don't have to worry about dust causing interference. But solar photons are dangerous, can kill your total visibility. And we are finding that some cosmic rays, the ones coming from the sun, are also dangerous. So you need to shield your detector against these things, and still you can have a dark matter. So if you put some kind of like lead or some kind of some material to protect the solar photons to enter or cosmic rays, still the dark matter can cross in there. So that's what they need to know. If they want to land this experiment to space, they need to be aware of the backgrounds. Because otherwise they will land this, they will put the experiment working, they will see a black, like no frames at all. So it will be useless. They need to control, they need to know how to shield the experiment against this background about it. So yeah, but if it's dark matter, if we shield the experiment, we see a reduction, and we suspect that it's dark matter, what people can do is do several measurements over the day. And because of we are traveling with dark matter halo, for instance, it's on Earth, there will be some directionality. So the visibility will change, will fluctuate over, will modulate along the day. Same if it's in an orbit of the ISS, International Space Station. If you know the orbit, you can compute how it modulates. This might help to discriminate this from other backgrounds. So there are ways to know, but it's hard. It's very easy to rule out things, but in this case, it would be hard to say this is dark matter. But I think there's no chance. Yeah.
More questions? No? Okay, I have many, but maybe better. Thank you for